Welcome to part 4 of the Mojo project. This video is about trying to understand why Mars is so much smaller than Earth. So just to get started, here's a kind of cartoon of the inner solar system. We have 4 rocky terrestrial planets. If you add them up, they make about twice the mass of the Earth. Then there's a wide belt, the asteroid belt. And then further out is Jupiter. Now the asteroid belt doesn't contain a lot of mass. If you add up all of the asteroids, they only are less than 1,000th of Earth mass. However, there's still some important information within the asteroid belt. The asteroid belt's orbits are dynamically excited. What we mean by that is that their orbital shapes are not all perfect circles, and their orbits are not all exactly in the same plane as the orbits of the other of the planets. And so this plot shows the distribution of the angle between the plane of the orbits of asteroids and of the Earth. In addition, the asteroid belt is radially segregated. It's not just a uniform distribution of stuff. The inner parts are dominated by S-type asteroids that are pretty dry, and kind of the outer parts of the main belt are dominated by C-types that have some water in them. So if we have a model that would, to explain the origin of the solar system, we need to explain the asteroid belt as well. Now, the simplest model to explain the inner solar system is called the classical model. It makes a simple assumption that we can treat the formation of the gas giant planets, Jupiter and Saturn, separately from the formation of the terrestrial planets. Now we know the gas giant planets formed fast while there was still gas in the disk, and that gas only lasted a few million years, whereas we know Earth's formation took 50 or 100 million years to complete. So the classical model assumes gas giants are already formed and they affect the growth of terrestrial planets. But here's what happens when you do computer simulations of the classical model. We form planetary systems that look kind of like this. Venus and Earth look pretty good, but Mars is way too massive. It's typically the mass of Earth instead of the mass of Mars. Mars is about 1/10 the mass of Earth, the real Mars, that is. Then the asteroid belts often have Marses stranded in there. And so this problem kept happening over and over in studies of the classical model, and this became called the small Mars problem. And what that means is that the Marses in our simulations are much bigger than the real Mars. And so we were struggling to understand why Mars is so much smaller than Earth. Now, a simple solution to this problem was proposed by Brad Hansen. He proposed that maybe the initial conditions for the growth of terrestrial planets were wrong. Instead of a nice smooth disk of rocky stuff, as the building blocks of the terrestrial planets, maybe there was just a ring. Maybe the terrestrial planets just formed from a narrow ring. And if that were the case, some of those bodies might have gotten kicked out of the ring. Mars would be one of these objects that was kicked out and effectively starved, whereas planets that grew within the ring, Venus and Earth, could grow big. And so this nicely explains why Mars is so much smaller than Earth. But then the question becomes, why should the terrestrial planets have formed from a ring? The first model to explain that was called the Grand Tack model. And it's actually a model that Morby and I both worked on many years ago now. And it's a very successful model. It's based on the idea that Jupiter and Saturn's migration early on, while the gas disk was still there, sculpted the inner disk of rocky stuff from which the terrestrial planets formed. And this image here is a snapshot from a computer simulation of Jupiter and Saturn migrating around within the disk. So what do we think that Jupiter and Saturn actually did? Well, here's a very simple explanation. So the vertical axis is the size of the planet's orbits, and the horizontal axis is time. So we think that Jupiter it first grew a core. When the core got big enough, it started to migrate. It started to migrate inward pretty quickly, then it cleared a gap, like we talked about in part 1, and transitioned to a slower mode of migration. And left to itself, Jupiter would just kept on migrating inward indefinitely. Meanwhile, Saturn was doing the same thing. Its core was growing a little farther away from the sun, so a little bit slower. Its core grew, it started to pile some gas on there and migrate also. And it migrated in quite quickly and caught up with Jupiter. Now, it didn't just bash into Jupiter. Instead, it was caught in an orbital resonance, where Saturn completed 2 orbits around the sun every time Jupiter did 3. And in this special configuration, Jupiter and Saturn's migration is no longer inward, but outward. And so in that case, Jupiter and Saturn migrate outward, and they again could keep going quite a ways, but the gas disk doesn't last that long. So the gas disk dissipated at some point, stranding Jupiter on an orbit close to its current orbit. So that's the grand tack model, and it naturally explains why Mars is small. Here's an animation of that process. So what we look here in this animation, the vertical axis is the orbital eccentricity. So you can see the little diagram on the side explaining that an eccentricity of 0 is a circular orbit, and a large eccentricity is a stretched out orbit. Now what we're going to see here is, starting from a disk, a continuous disk of rocky stuff, rocky planetary embryos and planetesimals, how Jupiter's inward then outward migration shapes that distribution. You can see Jupiter kind of migrates inward, and then it turns around and goes back outward. And once it's out of the way, what it leaves behind is a narrow ring of objects, narrow ring of rocky stuff, just like Hansen's ring, that can naturally form a big Earth and a small Mars. So the grand tack model does a really nice job of reproducing the inner solar system. Now, the Mojo contribution to this video has been to build other alternative models to the grand tack model to try to explain the origin of the inner solar system in different ways. Now let me describe the low-mass asteroid belt model. We think that the disk from which the planets formed started off pretty smooth. Especially the gas distribution was probably nice and smooth, and the dust distribution probably started off pretty smooth also. But when we look at pictures of dust around, within disks around young stars, we don't see smooth distributions. We see a lot of rings. And we think these rings are signs that dust drifts within disks and piles up in specific places. And it's possible that planetesimals form preferentially in those places where the dust is piling up. So the key assumption made in the low-mass asteroid belt model is that the planetesimals did not form smoothly across the inner solar system. They formed a ring with a couple Earth masses of material in the terrestrial planet zone. Then they only formed a small amount of planetesimals in the asteroid belt, and then they formed plenty of planetesimals formed further out in the Jupiter and Saturn region to explain the cores of Jupiter and Saturn. So based on this is kind of the starting conditions for planet formation, we know that we can reproduce the orbits of the terrestrial planets. The question is, what about the asteroid belt? This is not what our present-day asteroid belt looks like, either in terms of its orbital structure or its compositional distribution. The thing is, the asteroid belt can be repopulated by other processes happening within the disk. So when Jupiter and Saturn formed, they naturally scattered a lot of planetesimals from near where they were growing, and some of them end up getting implanted into the asteroid belt, and they have orbits very similar to the C-type asteroids. At the same time, especially on longer timescales, the formation of the terrestrial planets also implants a fraction of planetesimals within the belt as well. And so the asteroid belt itself can be repopulated from different places. But still, its orbital distribution is not right. So we need to explain why its orbital distribution is very excited like we see it today. And we found that a very small phase of chaos early in the orbits of Jupiter and Saturn can explain this. The idea is that just a very short phase of chaotic evolution in Jupiter and Saturn's orbits can have a big effect on the asteroid belt. It looks something like this. Just a little small wiggle among Jupiter and Saturn causes big shaking among the asteroids, and that can explain what we see today. So when you put these different pieces together, the low-mass asteroid belt model can explain the whole inner solar system, making it a viable candidate for how the solar system actually formed. There's another model for the inner solar system that's called the early instability model, and it's based on the idea that the solar system's giant planets underwent an instability. This is sometimes called the Nice model. Now, the idea is we think that the giant planets probably formed on a more compact configuration with an external ring of planetesimals that are shown in green here. But after a time, the giant planets' orbits went unstable, and they reshuffled, they cleared out this outer distribution, this outer disk of planetesimals, and reached their current orbits. And there's many different lines of evidence suggesting that this really happened. What's uncertain is the timing. When did it happen? And new thinking suggests that it could have happened very early. It could have happened almost immediately after the dispersal of the gas in the disk. And the early instability model looks at the effect of a very early instability in the solar system's giant planets on the formation of terrestrial planets. So now let me show you snapshots in a simulation of the early instability model. So what we're going to see is these snapshots in the evolution. The vertical axis is the orbital eccentricity. Again, you can see the scale on the side. And the horizontal axis is the orbital distance. And so the starting conditions are a whole bunch of building blocks of planets in the inner solar system and 5 giant planets. There's Jupiter, Saturn, Uranus, Neptune, and an extra ice giant that ends up getting ejected during the instability. So to start off, our starting conditions are when the gas disk dissipated. Then a few million years later, 10 million years later in this case, the instability was triggered among the giant planets. And that really excited the asteroid belt. The orbits of the asteroids get really excited. A lot of material from the asteroid belt got cleared out following that. And Mars, even the Mars region is affected. And within 20 million years, Mars's growth is completely stopped. But the growth of the Venus and Earth continues. And then, within a couple hundred million years, large Venus and a large Earth have formed and a small Mars. And you can see it compares quite well with the present day solar system, which is shown below. And so this shows that the early instability model can match the broad properties of the inner solar system. So that leaves us with 3 different possible solutions to the small Mars problem, 3 different evolutionary pathways of the early solar system that can explain why it looks like it does today. Yet they each have some issues. So these are kind of paths forward for future study. The low-mass asteroid belt model is really built on this idea of forming from a narrow ring of planetesimals. Is that realistic? We need to study that more. The grand tack model is built on the migration of Jupiter and Saturn, and we need to study that process in more detail. And the early instability model is based on the idea that this instability happened early. Now we need to study more carefully whether this is really the case. So we have 3 solutions, and that's where we're at for going forward.
Mojo!